Hello and welcome to this webinar on user-defined operators. What we're going to go through today is some of the reasons for using such operators and what you can do with them, what exactly they are, and then I'll show you exactly how to define some of your own, including some live-coded examples. Now, why would you define your own operators? There are a bunch of reasons for that. Data comes with a bunch of primitive operators, and many of them are very powerful. That doesn't mean that every possible operator ships with the product. Sometimes you want to do things a little bit differently, or by factoring out some code that is similar in two different places, you can avoid repeating yourself, or you might just want your expressions to look sleeker. Sometimes you use operators instead of functions to compute something that doesn't just take two arguments, but possibly another parameter or even a function parameter. So if it isn't part of the language out of the box, you've got to define it yourself. Let's have a look at what exactly is an operator. So an operator, I like to think of it as a type of factory. It's got an assembly line, and it either has one or two conveyor belts going in. That's the monadic operator has one, and the dyadic operator has two. And you can put things on these conveyor belts, and out on the other side comes an assembled item, which, depending on what you put on those conveyor belts, has a specific behavior. But everything that comes out of a specific factory is assembled in the same way. So here we are giving functions as operands to these operators, and out comes a bunch of functions that are related in how they do things, but are different in what exactly it is that they're doing. So I said operand. That's an important word to know. An operand is that parameter or conveyor, the thing that goes in the conveyor belt that the operator is assembled together with to produce something new. In this case, it's specifically a function, but it doesn't have to be just a function. In fact, it could also be an array. And these are called operands. So we've got function operands and array operands. And we can also mix and match them if the operator is designed for this. So at the bottom row, we've got some dyadic operators, and we can see that the right operand can be an array and the left operand a function, or the opposite, left is an array and right is a function, or even both of them can be arrays. Common for all of this is that what comes out on the other side is an assembly of this operator together with its operand or operands, and we call that a derived function. We can take just a derived function and we can give it a name, and then we can apply it just like any other function. I've used the word monadic and dyadic here, and we have to be a little bit careful because this pertains to the operator itself. We call them dyadic operators and monadic operators on whether they take two or one operand. However, the function that is derived can itself be monadic or dyadic, or in fact it could be both. It could be ambivalent, and you can use it in both a monadic or a dyadic manner. What I mean by a derived function being monadic, dyadic, or ambivalent: if it's ambivalent, then you could apply it with two arguments, and you can apply it with one argument, and both of them might work. However, the operator which has derived this function in both of these cases here is a monadic operator. If it's a derived dyadic function and you try to use it monetically, then the APL system will tell you that you can't do that. And similarly, if you derive a strictly monadic function, then the APL system will tell you that you can't apply it to two arguments. And so we've got monadic operators, dyadic operators, deriving monadic, dyadic, and ambivalent functions, giving us these 6 possibilities. And here are some examples of them. Right, so this is what operators do. Now, how do you define your own? All of these so far have been built-in ones. Let's look at normal function syntax. So we have tradfns and dfns. We're not going to deal with fully tacit functions and operators in this webinar. In the tradfn, the first line is a header. It's not code that's actually ever being run. Rather, it's kind of a pattern of how you would use this function. So in this case, we've got a result. So we're returning something, and then you could capture that. And then we've got a left argument and a right argument. In the middle, we've got the name of the function. Dfns work a bit differently. Here, you assign to a name for the dfn itself, and we just have alpha and omega, which are always the left and right argument, inside the dfn. This here is a dyadic function in both cases, both the tradfn and the dfn, because the header in the tradfn has both a left argument x and a right argument y, and the dfn's also dyadic. But really, dfns are a little bit special in that they're not really monadic or dyadic. They're kind of always dyadic. They can choose to use the left argument or not. But even a dfn that never mentions alpha anywhere can still be called with a left argument that it will then go and ignore. And you don't have to use omega either. Then it might just compute some expressions, ignoring entirely the arguments that you're giving it. So going from a function like this to an operator, we get something that has kind of similar syntax. We do take something on the left and something on the right, but this time it's an operand on the left and an argument on the right. So what we're seeing here are examples of monadic operators, and then we get from them a monadic function as well. Though again, for the dfn, you could give it a left argument, which it would then just ignore. Notice the parentheses in the header of the tradup. When you actually would use this, then you don't have to use these parentheses. But this is what tells the APL system that the operand on the left, which could be a function or an array, is grouped together with the operator to derive a new function. In a dup, there's no header, and instead the APL system will scan the source of this inside the curly braces, and if it finds any alpha alpha, then that's the left operand, and it will then use this code syntactically as a monadic operator. If there is an omega omega inside, then it will be a dyadic operator. You don't have to actually use them, though it seems a bit silly if you don't, but they have to be mentioned somewhere outside of comments and literal character arrays. So going from the monadic operator, giving a monadic function, we can add a left argument to have a monadic operator deriving a dyadic function. And that's simply just by mentioning in the tradfn header a left argument, just like we would do with a normal function. Then we can add a right operand as well, and that's that presence of the omega omega in the dup, and an additional name on the right side of the operator's name in the tradup. And then we can go and remove the left argument, giving us a dyadic operator deriving a monadic function. I'm going to demonstrate just writing some d-ups because they're easy to write on a single line, but everything else would apply as it normally would in a thread up as well. These are the type of things that I mentioned that could be useful to define operators for. And I'm going to show some examples of this. We'll have some utilities that you can use as you're programming. We are going to create some combinators that can compose functions in addition to the combinators or compositional operators that are already in Dyalog APL. And then we're going to add some more conceptual things to APL, meaning we're going to define operators that express things, much like APL can feel like Lego bricks that you're piecing together, and every brick is kind of its own thing. You're building up something from them. Every APL primitive represents a concept, and then you can put these concepts together to express a larger meaning. And of course, not everything is predefined, and we're going to define such concepts that call for operators, things you can't just do with a function. Alright, here is the APL session. Let's start off with those utilities. Let's say we have a function that determines if any character in its argument is a vowel. So we can apply this on the alphabet. Here's the alphabet. And while this is probably right, it can be a bit difficult to relate this Boolean vector with the alphabet because they don't line up properly. Sure, the A is a vowel, it's on top here, but we're using 2 character spaces for every Boolean value and only 1 for every character. That makes it a bit awkward to work with. So something that's very common to do is to take that argument and put it next to the result of the function application. This is just a nested vector. But now we can mix them, and that makes it a 2-row matrix. And now it's easy to see that the function in fact worked and pointed out our vowels. But it's awkward to write this. And it would be nice to have an operator that could do this automatically for us. And we can most certainly do that. Let's call it stack, because it stacks things on top, or just abbreviate it to S. I like using a naming convention that makes it easy for me to spot where my operators are, distinguish them from functions and arrays. And for that, I use underscores to indicate where operands would be. So in this case, where we're just dealing with one function, we want a monadic operator. And so I put an underscore on the left of the S to show that there is a slot on the left where an operand needs to go. If it was a dyadic operator, I would put an underscore additionally on the right, which is where the other operand goes. Right, so we're going to use the exact same formula as we did before. We mix the argument and the operand applied to the argument. That wasn't so hard. Let's try this. So we have vowel, and we are stacking it on top of the argument, the alphabet. That works beautifully. Now, not every function is monadic. Let's say instead that what we want is the index into the list of vowels, which means we'll get a 6 for all the characters that are not vowels. If we try to stack this, as we were doing before, then that doesn't quite work. What's happening here is that we're ignoring the left argument, and that means we're trying to do a monadic iota on the alphabet. And, well, not only is it a character array, but also it has 26 elements and would give us a 26-dimensional array, which isn't allowed, and that's what APL is complaining about here. So we could modify this. we could just insert that left argument where it needs to be. And now it just works. But going back to what we had before is now broken, because we're trying to use the left argument that isn't there. We could fix this by using a conditional, but there's actually a clever trick which is quite often used in situations like this for utility operators and sometimes functions as well. So what we want here is that the alpha should be present in this position when we have a left argument. When we don't have a left argument, we just want to pretend that the alpha isn't there. So what could we put in the position of this alpha which would make no difference at all? Well, an identity function would work. Yes, alpha was an array, but if it was a function, an identity function, then it would just work. So you can use the dfns syntax of a default left argument and say that if we're being called monadically, then we want alpha to be the identity function. Now, effectively, when there's no left argument, we get a right tag, an identity, same function here. We apply the operand on the argument, and then we do nothing to it, just return it like that. And now we can try both of these and see that they both work. That's a really useful utility function to have. At least, I think so. Here's another one. Do you know what this gives? Well, I have to think about it a little bit. It's not so obvious when the operand to a reduction isn't commutative. 10? You probably trust the APL system on it. But what's actually happening here can be a bit hard to tell. And sometimes we have an APL expression where it's not so obvious what exactly is going on. What are the arguments that this minus is seeing as it traverses the array? And for that, we can create an operator that will help us to get a view about what's going on. Monadic operator. We're going to modify the function such that it has a side effect of giving us a message about what's going on. We'll use the same trick as before, so that it can be used both with monadic and dyadic operands. Right. We do want to apply the function, and we do want to return a result. We just want the side effect of printing a message to us about what's going on. So let's start by computing the result. We're taking the left argument if it's there, otherwise it will just be applying the identity function on the result of the monadic application. We're applying the function as usual, saving the result. Then we want to do something with giving us this message, and then finally we want to return the result. What do we want to print here? Well, we should at least say what our left argument is, and also what our right argument is, and maybe the result would be nice as well. You might use this utility operator in multiple places, so we should probably identify which function is it that's reporting in right now. We can add another element for that over here. We can't just say output the operand, because this would just apply the operand to the arguments, and we're no better off. Instead, we want to analyze this name, and now we have got this new system function called ATX, extended attributes, and you can find out all kinds of things, including about this name alpha alpha. You can look it up. They're numeric, these codes, but 62 is about the best source that we have, the actual code that's being applied. And finally, we should probably separate the right argument from the results so that we know what's what. And we could do that, for example, with a red arrow, kind of indicating that it gives this result. And that's it. Now we can go up here and modify t, or modify minus by inserting this underscore t, and that will make minus, it's still the same minus, but it will report out every time it's being applied what its left argument, right argument, and results are. So here you can see that what's happening is that we're actually inserting minus in between the elements of the array, and then evaluating it like a normal APL expression, that is from right to left. So we have 1 minus 5, and then 4 minus that, and then 1 minus that, and then 3 minus that. And that explains the 10 that comes out. So this is a really useful operator, something that I use a lot to inspect things. Let's move on to some combinators or compositions. Since version 18.0, we have a very good set of combinators, but there are still some that you might be missing. Consider set intersection. So the without function gives us all the elements that are in the left but not in the right. And if we commute it around, then we get the opposite. If you wanted like the full set difference, so all the elements that appear in any argument but not in both of them, that is to say kind of a set XOR, an exclusive OR, then we want both those that appear on the left but not on the right, and also those that appear on the right not on the left. And we want to combine those together. So it is the same function that's being applied, but it's being applied both normally and with the arguments swapped or commuted. This calls for an operator. Somebody came up with a name across for it. I like that. Let's call it A. And now it's dyadic, so I'm going to use 2 slot indicators, 2 underscores. Again, the underscores don't actually do anything. It just helps me understand what the syntax of this is. And so what we want is we have a left argument and a right argument. In this case, there's not really any point in making it applicable in the monadic case, because only a dyadic function you can commute the arguments and it's still being meaningful. Otherwise, if it would come like a self, it would do it on the self, that means something entirely different. So let's not bother with that. And then we want to return something. So we have the combination. We'll take that as the left operand. In this case, it would be concatenation or union, but it could of course be anything. And on the left, we have the direct application of the function. On the right, we have the commuted application of the function. So all these 3 are functions. This is the operand, this is the commuted operand, and this is the other operand, the combination operand. And these form a fork, a 3-train. And so we're applying this to the arguments, and this to the arguments, and this in between the results. That's exactly what we want. Now we can try it. So we want the union across the set differences. And there are of course other things you could do with this as well. And you can modify it to suit your needs. You might want to commute on the left and have the regular function on the right, for example. Here's another one. It's classically called the hook. It comes up actually a lot. This is when you want to apply a function, a dyadic function. You want to use the same argument twice, but you want to, so to say, pre-process the argument as one of the arguments. Yeah, this sounds complicated. So let me give you an example of that. Let's have some character vectors. And I want to see whether or not they are palindromes. That is, you can read them forwards and backwards and they still are the same. So for each one of them, I want the reverse of the argument, and I want the argument itself. So here we have it. We have a function applied to the argument and with just the argument itself, and then another function applied in between those two. And this gives us the whether or not each of these are palindromes. Notice this pattern. A function applied, and then the argument itself, and then between them something else. We can define this as an operator. And the reason I'll call it hook is because if you think of it as a tree structure, it's kind of lopsided. There's like a longer leg on this side than on this side. So you can kind of see it as a fishing hook. The way we'll define it is quite simply the same pattern as here. We have an operand on the left, and we're applying that to the argument. And then we have an operand to the right with the argument itself on the right. So this is exactly the same pattern as we had up here, but just with the names of the operands and the argument. And now we can try this. So we want the reverse hook with match on each. I really like how this reads. This compositional operator, it almost doesn't need a word when you read out what's going on here. We're simply asking, does the reverse match for each of these? And so too, there are a lot of patterns, but when you try to read them out what you're trying to do, it doesn't really take a word even. It's just so fundamental. Remember the stack? We could use a stack for this as well. So here we can see for each one of these elements, these character vectors, whether or not they're palindromes, pairing them up. Oh, but we can see something else as well. We could use this to filter. Let's say we only want the palindromes. So we've got 0, 1, 0, 1, 0, and we can use replicate with this. But notice the pattern now. What is replicate really doing here? The Boolean vector was the result of applying a function, namely the reverse hook match each. And we want that on the whole argument, this vector of character vectors. And on the right of replicate, we just want the unmodified vector of character vectors. Well, this calls for a hook again. So, hook will replicate. And we can read this as, does the reverse match filters? So if we read replicate as filters, again the hook doesn't really take a word. So the reverse match of each, does the reverse match of each filters? A very useful little operator. Right, let's move on to something else. Let's move on to these concepts, these Lego blocks. You might have used the power operator. The power operator is very good and powerful, but sometimes it doesn't quite do what you want. Firstly, if you use a function right operand, then it will apply the left operand until the condition holds. And that condition is in terms of the previous result and the next result. So for example, if you do power match, then it will keep applying an operand until two consecutive applications give the same exact result. Now this is problematic because maybe the condition for stopping is already fulfilled right from the beginning, and the power operator will always apply your operand at least once. Furthermore, it's kind of awkward to state things in terms of until. Very often you want to do something while something is true. So let's create an operator that will do this for us. The calling syntax we want is an optional parameter on the left, and then we have a function. That's the function we want to apply with over and over again. And we want to do that while some condition is true, starting on an initial argument. And that condition, we just want it in terms of where we're up to now. So we start by asking it on the initial argument, and if it doesn't hold, if it's true, then we keep applying the function, and then we try the condition again, and then we apply it again until it doesn't hold true anymore, in which case we're done, we stop. It's actually pretty straightforward to define this. We'll use the same trick again for making it ambivalent, the derived function. And then we ask, the right operand is the condition. Is the condition on the argument true? If so, then we want to keep going. So this is our derived function with the operands already bound to them, with the left argument, or it might not be there, just a no-up function, and the right argument. But we want to then apply the left operand before we continue, possibly with a left argument as well. And finally, if the condition doesn't hold, then we're done. We just return the current value. We can try this. Let's say we multiply by 2 while the argument is less than 100. And we'll start off with 4. 128. Yeah, we overshot the target of 100. Why exactly? Well, let's look at what multiplication saw. So we can use our tracing operator for that. We can see that we multiplied by 2 to get 8, then 16, then 32, then 64, and the condition still didn't hold. Then we went to 128, the condition held, and we're done. 28 is the first value after the condition stopped being true. We can even look at what the conditional is doing. So now we're tracing two different functions. So we can see for less than 100, we started off by checking the initial argument, and it is less than 100. So we multiply by 2 to get 8. 8 is still less than 100, so we kept going until the very end. 64, still less than 100, and then 128. We checked that, and we found that the condition is not holding anymore. And we returned 128. So that's a while operator. And you could use control structures for this, but if you want a more functional way of stating it, then you could use this as a while. Another thing we might want to do is when an error happens, instead of going into a whole error trapping, we already know what kind of result we want. We might want to apply a different function if the erroring function didn't work out. Here's an example. We divide by 4. That's fine. But dividing by 0, that gives us an error. But maybe whenever we divide by 0, I actually just want a 0 back, or some other value. So instead of having to trap this and then return something else, wrapping the whole thing, we can write an operator that is kind of like an else, an error else. We start off the same way to make it work on both monadic and dyadic operands. And then we make an error guard. If any error happens, then we'll use the alternate function instead, the right operand. And once that error guard is up and running, then we'll attempt to apply the normal function, the left operand. We can try this. So we can say, try to divide, but if it errors, then multiply instead. Because multiplying by 0, that will just give us 0. And that works. And it's still normal multiplication in all other cases. But maybe we don't really want the function. Maybe we just want the value. Well, we could put in a constant function here. So let's say we want the word nan. But it seems a bit silly to have to wrap a constant in a function just to use it like this. And so we can expand on our or modify our operator so it's a bit more versatile. We can use a kind of clever trick for that. This might seem very silly at first, but bear with me for a moment. Instead of using the left operand, I'll use a train, a 3 train, a fork. And it looks like this. That's all right. What happens here is the outer function are being applied first. So the right function between the arguments, if there is a left argument, or just applied to the right argument, that returns the right argument. And this one also returns the right argument. So now we have the right argument twice, one on the left, one on the right, and the middle one then selects the right one. Yeah, I know, very silly. It's the same thing as just returning the right argument. Turning that middle tag around, we now choose the left one, but it's still the same. But here's the thing. Let's, instead of using the right tag, we're going to use the left operand. Sorry. The right operand. That's the one we want to fall back to when we have an error. Now what happens, let's assume it's a function at first. So it's the same fork as before. This gives us the right argument, and this applies the function between the arguments, and then we choose the left one. So it's exactly the same thing as if we hadn't done this at all. And this is we call it an FGH train, or 3 function train. But the thing is, 3 trains can also be so-called AGH trains, which have an array as the left tine of the fork. In which case, that value is just being used as left argument to the middle function. So now what happens? The function on the right selects the right argument. That doesn't actually matter. Could have been anything. And then we have this array here. And so we're applying the left function with the right argument as right argument, and with this value, this array, as left argument, and we just return that. So we just ignore the right argument. So this construct is either an FGH train or an AGH train, depending on what kind of right operand it is. And that allows us to use either kind of operand in a single expression. We can try it. So this is with a function. We can also use the multiplication for that sake. And now we can do it with an array operand as well. We just need to separate the right operand from the right argument, either with a function or with parentheses. So that's an error-else operator, you could call it. Finally, let's consider a simple definition of factorial. Yes, APL has its own factorial function built in, and it has a much larger domain, but this is just for demonstration purposes. We can define factorial as the product of the indices. Well, that's great. We can apply that on 4 here, and we could apply it on 5. But what happens, notice that this is a scalar function. It's a scalar function because it takes a single number and transforms it to another single simple number. But if you try to give it an array of numbers to apply to, we get something that's entirely misguided. Why is that? It's because we're just applying the functions in order. So we're applying the monadic iota, that's the indices, which returns us a table of all the indices in an array of shape 4 by 5. And then we're multiplying the rows by that, and it's not really meaningful. Well, we can just apply this function on each one. That works fine. But what happens if the structure is more nested? And again, a scalar function will just apply to all the numbers that are found anywhere in this array. Well, that didn't work well. But we can add more eaches. But there's not really any end to it. Yeah, sure, it's working, but how many eaches do we need? Infinitely many eaches? We can write an operator that takes a function and makes it scalar. I'll call it underscore 0 because it applies to scalars, and scalars have simple scalars have depth 0. I'm going to use a little bit of a trick here. We know exactly what structure the result is going to have because it's a scalar function. It transforms single numbers to single numbers. So we know that the result has the exact same structure as the argument. We can initialize kind of a container for the result just by cloning our argument. And then we can flatten entirely, we'll enlist the argument. Now we know we have a simple vector, but we have lost all the information about the structure. Since it's a simple vector, we can apply our operand on each one individually. We don't need any more eaches because there's no deeper structure. And then we just need to put all these values back where they came from. For that, we can use selective assignment, where the selection is the enlist of R. We couldn't use omega here because we're not allowed to modify the argument to a dfn or dob. So this puts all these values that are simple as a vector into the slot they came from. Of course, this has the same value and same length as this because we're applying it one-to-one on that same enlisted thing. We could also use R over here. It doesn't make a difference. And now that we have updated R to contain our result, then we just need to return it. And so we can apply our underscore 0 operator with this function, which is not defined so that it can be a scalar function, but is actually supposed to be a scalar function, and that makes it a scalar function. So that's a useful operator. Note that it only works for monadic application, the monadic scalar application of a function. If you want dyadic, then you need to make it a little bit more complex. However, you can actually copy that in. There's a function called perv, from like pervade, that pervades all structure in the dfns workspace. And it looks like this. It's a recursive function. I'm not going to explain it now, but you can look at the notes in the dfns workspace, notes.perv, and it explains everything about it. So these are our examples of operators for today. We use them to apply functions in similar ways. We had our utility functions that were just applying the function with the side effect of printing out what's going on. So for every function that we might use with that operator, they're just being used in the same way with a side effect. And we have used, for example, the hook operator to create quite nice looking expressions. And we defined the while operator for what we needed as well. So that worked out quite nicely. That's all I have for you today. You feel free to ask any questions in chat if you're watching this live. While I'm waiting for that, just a little bit about what's coming up. Next webinar, June 23rd. Don't know yet what it's going to be about, but we'll figure it out. Also, don't forget the very nice sessions that are happening on the BAA on Zoom every other week. Generally, they're just open sessions, and people come and either present or discuss things. And there are even more APL-related activities going on. You can find out about those on the APL Wiki. So with no questions having come in, all that remains to do here is to say thank you for watching.